Welcome. Welcome to this talk on optical measurement in dam spillways with a down-to-earth review of pros and cons. My name is Hubert Johnson and I'm based at the University of Queensland in Brisbane, Australia. As a starting point, we may wonder how many people have seen physically in person a large spillway in operation in their life, and how many people among these have performed physically some field measurement during a large spillway operation. The context of this talk is the recognition of hydrological and hydraulic engineering extremes, with, for example, in Australia, hot temperature and long droughts, but also extreme rainfalls, with a greater recognition from the general public for the need for water security and flood protection, particularly in our society with its growing population. Despite what some social media suggest, dams and reservoirs constitute the most efficient means to provide both water security and flood protection. Dams, which must be equipped with a spillway to pass safely floodwaters above, below, around, within the dam. Spillways, which are two key hydraulic engineering roles: safe conveyance and safe energy dissipation. But what do we know really about prototype spillway operation beyond visual, qualitative observations and physical modeling too often conducted in small-sized facilities? We may wonder, why do we need field observation and measurements? First of all, because nature is the final jury. Because there are also some opportunities. For example, there have been a number of spillway overflow in the last 10 years in Eastern Australia. But possibly more importantly, because we need to remember that water engineering is not a desk job for desk jockey. Field measurements were conducted at two sites, the Chinchilla weir and the Hinge Dam Spillway, both located in Queensland, Australia. The Chinchilla weir is a minimum energy loss weir with a smooth converging spillway chute with a design discharge for 850 cubic meter per second. Also, the notion or the definition of this design discharge in this case is for bank full. The second site, the Hinge Dam, is located in the Gold Coast hinterland. It's a steep step spillway chute with a design discharge corresponding to PMF of nearly or more than 4,000 cubic meter per second. This video illustrates the operation of the Chinchilla weir on the 27th November 2021 for a discharge at the time of about 121 cubic meter per second. This second movie, taken in December 2021, looked at the flow on the left spillway bay, flowing from the top to the bottom with a hydraulic jump in the foreground bottom. This video illustrates the clear water flow upstream, the self-aeration down the chute, and of course a very strong turbulent flow in the hydraulic jump roller. This video illustrates the Hinge Dam Spillway on the 23rd of March 2021 for a unit discharge of 9.1 square meter per second. Again, we see clearly the non-aerated flow upstream and the white water further downstream. In this particular video, the image quality is not very good because it was raining very hard at the time of the movie. The second movie of the Hinge Dam was taken in February 2022 for a discharge of 52 cubic meter per second. It's a movie recorded at 120 frames per second and replayed at 30 frames per second, 1/4 of the normal speed. It illustrates in particular the very intense and sometimes explosive processes taking place near the inception of self-aeration and in the white water area. Surface velocity measurements were conducted using an optical technique, with here some of the setups on the left at Chinchilla weir, on the right at the Hinds Dam. Typical example of surface velocity data are shown here at the Chinchilla weir. On the left, we see the surface velocity in blue as a function of the vertical axis, of the vertical elevation, which is the vertical axis of the graph. The surface velocity, thick blue data, are compared with the ideal fluid flow velocity in green and the backwater calculation for the converging chute in red, with the optical data showing some nice agreement in terms of the surface velocity in the air-water flow region with the backwater calculations. But on the other hand, very poor data quality in the non-aerated flow region because of the surface glare that we see on the top right. This graph illustrates on the other hand the contour map of the streamwise surface velocity at the Hinds Dam. On the top, it's time average surface velocity. On the bottom left is the standard deviation of the streamwise surface velocity, providing some nice detail in the non-aerated surface flow upstream of the inception region. But on the other hand, very poor data in the air-water flow region at the Hinds Dam. The experience at these two sites highlighted a number of challenges with the optical flow technology and the metrology. Field observations were conducted between 1992 to 2022, but surface velocity were only obtained since 2013. One of the key parameters is light. Light is critical for any optical technique, but in the field, it cannot be controlled. The second challenge is validation or validation because of the inexistence of independent validation datasets and the need for a hybrid validation against theory and fraud-scaled physical model data. And for example, on the right, a comparison at the Hinds Dam between the surface velocity, optical surface velocity in green and blue, the ideal fluid flow theory in red, and fraud-scaled laboratory data, which are the black cross. But at the end, there remains a question about the field data quality. How can we assess the data quality? A third key challenge is the resource requirement, not only the field equipment, we need to bring a lot of equipment in the field, but also the expertise of the staff, the human resources, staff which need to have a lot of enthusiasm, particularly when it's pouring rain, not to mention safety and good luck. What did we learn from these practical experiences and challenges? Access, both physically and optically, is essential. Personal safety. We need a good viewing point with a fixed study location, typically a study tripod. We have no control on the atmospheric conditions, rain, mist, light. The best results were obtained with high-quality lenses and SLR camera sensor, using prime lenses and typically long lenses. We need to have high-quality and accurate ground reference points. And we need to remember that we have no truly independent validation, and we always need some luck. So, in conclusion, in a recent forum, senior dam engineers acknowledge that our design procedure for major hydraulic structure is often all too optimistic. On many occasions, the expression of one's experience on the extreme of hydraulics behavior is often countered with skepticism. It could not happen to my dam, my spillway, my bridge. We need more information on prototype spillway operation. Surface velocity measurements were successfully conducted at 2 large dams during major flood events. It demonstrated the potential for optical measurements, highlighting that the flow field is not one-dimensional but three-dimensional, with streets of high velocity and canyons of low speed, in turn leading to concentration zone of kinetic energy, with potential implication in the sealing basin design and operation, possibly with the need for an additional safety factor or the need for novel sealing basin design. We learn that some of the 3 key challenges are light, validation, and resources. And good luck. At the end, a key focus of this talk and a key message to every water engineer is water engineering is not a desk job for desk jockey. This presentation was presented in Brisbane in 2022 at the HWRS and is supported by a peer-review conference paper. Additional relevant references are listed here. Thank you very much